Welcome to the video help with physics problems for Physics 1B. In this video we're going to be covering homework set 5, part 1, which is everything under the headings interference and diffraction, diffraction limits of resolution, and gratings and spectra. For 1221 students this is questions 1 to 6. For 1231 students this is questions 1 to 8. Problem 1. This is a 1231 only problem. Part A of this question asks how many complete fringes appear between the first minima of the fringe envelope on either side of the central maximum for a double slit pattern if lambda is equal to 550 nanometers, D, which is the spacing between the slits, is equal to 0.150 millimeters, and A, which is the slit width, is equal to 0.030 millimeters. So what's going to happen is the image we're going to see is going to be the double slit interference pattern imposed over the top of the diffraction around the single slit. So what we'll end up with is the single slit pattern, which will look something like this. And over inside this central envelope and these other fringes, we'll have our double slit fringes, which will be like this. So the single slit will determine where these first minimums are. These minimums will satisfy the equation A sine theta is equal to 1 times lambda. That will give us the theta at which this minimum and this minimum occurs. And then what we need to do is count up how many of these maximums from the double slit occur within that. So let's solve this and work out where these minimums are. We know that sine theta is equal to lambda, which is 550 times 10 to the minus 9, over A, which is 0.030 times 10 to the minus 3. So that tells us that sine theta is equal to 0.0183 with a repeater. So these threes keep on going. So that's the sine theta. Now what we need to do is work out how many of these maximums occur for thetas less than this sine theta. So to do that, we know that d sine theta is equal to n lambda, tells us how many maximums occur in a double slit pattern. So what we're going to do is solve this for n. So n is equal to d sine theta over lambda, which is equal to 0.150 times 10 to the minus 3 times sine theta, which we've got over here, 0.0183 repeater, over 550 times 10 to the minus 9. Solving that, we end up with 4.9999. Okay, so now the question asks how many complete fringes will we see? So this will be the n equals 0, and then we'll have n equals 1, n equals 2, n equals 3, n equals 4, and n equals 5 will be directly over this minimum. So we're not going to see this one because it's at a minimum. So we'll see 1, 2, 3, 4, and then the central one on this side, and then the other 4 on this side. So 4 plus the central one, which means that we will see 9 fringes. And that's complete fringes. Now part B of this question says, what is the ratio of the intensity of the third fringe to the side of the centre to that of the central fringe? So to do this, we're going to need to use our intensity equation. To get the intensity when we're considering the diffraction with a double slit, we need to put together the intensity equations for a single slit diffraction pattern with the double slit interference pattern. So both those formulas are given on your formula sheet, but you need to put them together. So what we have is the intensity is equal to I max times cos squared pi d sine theta over lambda. This tells us the intensity of a double slit pattern, and then we need to put in the intensity of the single slit diffraction pattern, which is given by sine beta over 2 over beta over 2 squared, where beta is equal to 2 pi a sine theta over lambda. Okay, so let's just start by working out what sine theta is. We know this is the third maximum, so we can use this equation here and substitute in n equals 3. So we have sine theta is equal to 3 lambda over d. Okay, so let's just work out what beta is for a start. Beta is equal to 2 pi a times sine theta, which is 3 lambda over d, and then this is all over lambda. So these lambdas will cancel out, and we'll end up with 6 pi a over d. So this is our beta, and let's just look at what happens inside this cos. We have, let's call this alpha. And alpha is equal to pi d over lambda times sine theta, which is 3 lambda over d. So these d's cancel, and we end up with alpha is equal to 3 pi. So let's now substitute these in. The intensity at the third fringe will be equal to I max, that's the central intensity, the intensity here, times cos squared 3 pi times sine of beta over 2, so that's sine of 3 pi a on d over 3 pi a on d, and this is all squared. So solving this, we've got I max cos squared 3 pi. Cos of 3 pi is minus 1, squaring that we've got 1, and 3 pi a on d is equal to, substituting in 0.03 here and 0.15 here, we don't have to convert from millimeters because we're dividing, we get 1.8849 when we solve that on the calculator. So we've got sine of 1.8849 over 1.8849 all squared, and then solving this on the calculator we end up with I max times 0.255. So our answer is 0.255 times the maximum at the central fringe. This is problem 1 for 1221 or 2 for 1231. In this problem we're given a diagram and we're told that lambda is equal to 440 nanometers. We're told that the light passes through a double slit setup, and this diagram shows us the intensity versus the deflection angle in degrees. This angle here is 5 degrees. And we're asked in part A to calculate the slit width. So the slit width, we can work this out by looking at where this first minimum in the diffraction pattern occurs, because the slit width is what's responsible for the diffraction part of this. So the diffraction minimums are given by the formula A sine theta is equal to n lambda, or m if you want. And this is the first minimum, so this is m equals 1. So we've got A is equal to lambda over sine theta. And you can see on the diagram that the first minimum occurs at approximately 5 degrees. So we've got that the slit width is equal to 440 times 10 to the minus 9 over sine of 5 degrees. So solving that on the calculator, making sure that the calculator is in degrees, you end up with 5.048 times 10 to the minus 6. So this is equal to 5.0 micrometers as the slit width. Now part B asks us what's the slit separation. The slit separation is D, so we have to use the formula D sine theta is equal to m lambda. So this first maximum here, this is the m is equal to 0, and then we've got m is equal to 1, m is equal to 2, m is equal to 3. Now you can see the m is equal to 4 maximum is going to be here. There's no maximum there because it's at the minimum of the diffraction pattern. So we have m is equal to 4 here. So m equals 4 corresponds to 5 degrees. So substituting that in, we've got d is equal to 4 times 440 times 10 to the minus 9 over sine of 5 degrees. Now this is going to be 4 times as big as this, so we'll end up with 20 micrometers, which, this will be useful later, this is equal to 4a. Okay, now part C says verify the displayed intensities of the m equals 1 and m equals 2 interference fringes. So we need to verify this intensity here and this intensity here. The maximum intensity, the graph says, is equal to 7. We need to use the formula for when we have a diffraction pattern and an interference pattern. So to do that, we combine the two formulas on the formula sheet, and we end up with the intensity is equal to the maximum intensity times cos pi d sine theta over lambda, and this is cos squared, and then we need to times that by sine beta over 2 over beta over 2, and this is all squared, where beta is equal to 2 pi a sine theta over lambda. And let's refer to this as alpha. So let's start by solving for the m equals 1 case. When m is equal to 1, that's this one here, we have, using the formula for interference fringes, sine theta is equal to m lambda, which is 1, so that's lambda over d. So now what we can do is we can substitute this sine theta in and find alpha and find beta. So this tells us that alpha is equal to pi d on lambda times sine theta, which is lambda over d. So this is equal to pi. And beta is equal to 2 pi a over lambda times sine theta, which is lambda over d. These lambdas will cancel. Now let's replace this d with 4a. So these a's cancel and we end up with pi on 2. So now we can substitute this in to get that intensity. So we've got I is equal to I max cos squared pi. So this will be minus 1 squared, which will just be 1 times sine of pi on 4 all over pi on 4 squared. So solving that on the calculator, we end up with 0.81 times I max. And then the I max we said was 7 approximately, so this should be approximately equal to 5.7. And if we look at this, you can see this is approximately 5.7, that's just below the 6. So that one is correct. Now we were also asked to verify it for the m equals 2. So when m equals 2, let's make some more space, we've got sine theta is equal to 2 lambda over d, which tells us that alpha is equal to lambda d on pi times 2 lambda on d. So this is equal to 2 pi. And beta is equal to 2 pi a over lambda sine theta, so that's 2 lambda, and instead of d let's put 4a. So these numbers cancel, the a's cancel, the lambdas cancel, and we end up with beta is equal to pi. So our intensity is equal to the maximum intensity times cos squared of 2 pi, so this will just be 1 squared times sine pi on 2 over pi on 2 all squared. And so solving this on the calculator, we end up with 0.405 times I max, and then substituting in the 7, we end up with 2.8. And looking at the intensity here, you can see it's just below 3, so that looks reasonable. So we verified those two intensities. This is problem 2 for 1221 or 3 for 1231. In this problem, you have two car headlights that are 1.23 meters apart. And the question asks us, at what maximum distance will the human eye be able to resolve these? And we're told that we can assume that the human eye is a circular aperture with a diameter of 5 millimeters. So to answer this problem, we're going to need to use Rayleigh's criteria. Which says that to resolve two sources, the central maximum of 1 falls on the minimum, on the first minimum of the other. This gives the limiting case. So this gives the closest two sources can be in order for us to resolve them. So this gives us the formula. The minimum angle between the sources is 1.22 lambda over d, where d is the diameter of the aperture. The 1.22 comes about because it's actually a circular aperture, not just a single slit, and the lambda is the wavelength. So we'll just need to use this equation to work out the solution to this one. So we've got that the minimum angle between these two sources is 1.22 times 550 times 10 to the minus 9. That's the wavelength, which we're told in the question, and d is the 5 millimeters. So solving this, we get 1.342 times 10 to the minus 4 radians. This is the minimum theta here. And what we want to know is this distance, let's call it x, of the lights from the eye. So we can write from this tan of theta min on 2, so that's considering this triangle here, is equal to the 1.23 on 2 over x, and then tan theta is approximately sine theta, which is approximately theta, so this is approximately theta min on 2, so these 2's will cancel out, and we have x is equal to 1.23 over theta min, where here's our theta min here, so we're just substituting that in. When we solve that on the calculator, we get 9.2 kilometers. So we should be able to resolve these headlights when they're 9.2 kilometers away. Okay, now we're going to do problem 3 for 1221 or 4 for 1231. This problem, part A, states how small is the angular separation of two stars. So we've got two stars, and we want to work out their angular separation here, theta, if their images are barely resolved by a telescope with a lens diameter of 76 centimeters, so 0.76 meters, and a focal length of 14 meters. And we're told we can assume lambda is equal to 550 nanometers. Well, we'll need to use the Rayleigh criterion again. The minimum separation they can have and be resolved is given by 1.22 lambda over d. And so this is equal to 1.22 times 550 times 10 to the minus 9 over 0.76. And solving this on the calculator, we end up with 8.8 times 10 to the minus 7 radians. Now part B says find the distance between these barely resolved stars if each of them is 10 light years distance from the Earth. Okay, so let's call this distance between them x. This distance here is 10 light years. And we've got a right angle triangle here with theta min on 2. So we have sine theta min on 2 is equal to opposite, which is x, over the hypotenuse, the 10 light years. Now the distance between them is 2x, because each of these is x, it's symmetric. So what we're trying to find is 2x. Now to make it easier, let's use the normal approximation. Sine theta, because theta is small, is approximately sine theta min on 2. So we have 2x is equal to theta min times the 10 light years. And now all we need to do is substitute in. So we've got 8.8 times 10 to the minus 7 times the 10 light years. Now that's 10 times the speed of light, which is 3 times 10 to the 8, times the number of seconds in a year, which is 365, which gets it into the number of days, times 24, the number of hours, times 60, the number of minutes, times 60, the number of seconds. So solving this on the calculator, we end up with 8.4 times 10 to the 10 meters. So that's the separation, that's 2x, the distance between these two stars. Now part C, for the image of a single star in this telescope, find the diameter of the first dark ring in the diffraction pattern as measured on the photographic plate placed on the focal plane. Assume that the star structure is associated entirely with the diffraction at the lens aperture and not with the small imperfections. Okay, so what we've got here is the light coming through our aperture. Theta min gives us the angle between the central maximum and the first minimum here, and the distance between our aperture and our focal plane is 14 meters. So we'll be considering this triangle here, and what we'll actually want to get is the diameter. So this here is the radius, and we'll need to double it to get our diameter. So we have tan theta min, which is approximately theta min, is equal to r over 14. We know from our Rayleigh criterion that theta min is equal to 1.22 lambda over d. So this tells us that the radius is equal to 14 times 1.22 times 550 nanometers over the diameter, which is 0.76. So solving this, we end up with 1.236 times 10 to the minus 5, which tells us that the diameter, 2r, is equal to 2.5 times 10 to the minus 5 meters. So that gives us the diameter of the first dark ring. Okay, we're on to problem 4 for 1221 or 5 for 1231. In this problem, we've got a ruby laser with a wavelength of 694 nanometers. It goes through a circular aperture with a diameter of 2 centimeters. Now we're told that this is aimed at the moon and that we can assume that the spread is due only to the diffraction of this aperture. So we've got on our moon theta min here, and it's a distance of 380,000 kilometers from the Earth. And so we can get the radius of our beam here, the distance between the central maximum and the first minimum, if we can work out theta min. Now, the theta min is going to be determined by the Rayleigh criterion. So we have theta min is equal to 1.22 lambda over d. So this is equal to 1.22 times 695 times 10 to the minus 9 over 0.02. So solving that, we get theta min is equal to 8.83 times 10 to the minus 7 radians. So now we can use tan theta min is approximately theta min. Using the geometry here, that is equal to the radius of the beam over 380,000 times 10 to the 3. And so substituting in, solving this for the radius, we get that the radius is equal to 16 kilometers, but we've been asked to find the diameter, so the diameter is double that, it is equal to 32 kilometres. This is problem 6 for 1231 only. In this problem, we're asked to prove the expression I is equal to 1/9 I max 1 plus 4 cos phi plus 4 cos squared phi, where phi is equal to 2 pi d sine theta over lambda for the intensity pattern for a 3-slit grating. So that's a grating with 3 slits, 1, 2, 3. And we're considering the intensity at some point on the screen P here. We're told that we can assume that D is a lot less than lambda. D is the space between the adjacent slits, so this is equal to D. So we consider the light rays travelling to P. Now this angle here is given as theta, and so this angle up here is theta, and so the light rays from the second slit have travelled an extra distance d sine theta, and the light rays from the third slit have travelled a further distance d sine theta. So the difference between the light from 1 and 3 is 2d sine theta. Now we can write an expression for the electric field arriving at point P due to each of these different slits. So we've got that the light through slit 1 is given by E naught sine omega t minus phi, and then E2 is equal to E naught sine omega t, and E3 is equal to E naught sine omega t plus phi. Now phi is dependent upon the path difference between these three parts. The difference between the distance travelled from point 1 and point 2 is the same as the distance travelled from point 3 and point 2, only in the opposite direction. Point 3 has to travel an extra distance of d sine theta, and point 1 travels less by d sine theta. So that gives us the minus phi up here and the plus phi down here. And so the optical path difference is equal to d sine theta. That's just what we've said here, the d sine theta. And so this tells us that the phi is equal to d sine theta over lambda times 2 pi. So this is getting it into radians. This tells us what fraction of a wavelength this optical path difference is. So now we can use the rule of superposition to add up all the contributions of the electric field at P. All we need to do is sum these together. So we've got that the electric field at P is equal to E naught, that's a common factor, sine omega t minus phi plus sine omega t plus sine omega t plus phi. And what we're going to do now is use the mathematical relationship. Sine A plus sine B is equal to sine A plus B on 2 cos A minus B on 2, and this is all times 2. So we'll call this one A and this one B. So we've got EP is equal to E naught. Now we've still got this sine omega t, and this sine A plus sine B becomes plus 2 sine. Now when we add A and B, we get 2 omega t divided by 2, so this is omega t, times cos of the A minus B, so that's 2 phi on 2, so that's phi. So we can write this as E naught sine omega t outside of 1 plus 2 cos phi. And so the maximum value, E max, will equal E naught sine omega t times 3, because the maximum value this can have is 3. Now what we're asked about is the intensity, and the intensity is proportional to the electric field squared. So we have that EP squared is equal to E naught squared times sine squared omega t times the square of this. When we square this, we get 1 plus 4 cos phi plus this squared, which is 4 cos squared phi. We can rearrange this equation here to tell us that E naught sine omega t is equal to E max on 3. And so we can replace this with E max squared on 9 times 1 plus 4 cos phi plus 4 cos squared phi. And E max squared is just I max, so this is equal to the maximum intensity over 9 times 1 plus 4 cos phi plus 4 cos squared phi. And that, as you can see here, is what we were asked to show. This is problem 5 for 1221 or 7 for 1231. In this problem, we're asked about the smallest wavelength interval that can be resolved using a diffraction grating. To start with, let's consider what we see coming out of a diffraction grating. A diffraction grating will give us large maximums with a few minimums in between them. These maximums can be found at d sine theta equals m lambda, the same as for a Young's double slit. But between these maximums, we've got n, capital N, standing for the number of lines in the diffraction grating, minima. So the minima are found at d sine theta equals m lambda over n. So let's let this maxima be at m lambda over d, so that's sine theta is equal to m lambda over d, and this one here is at sine theta is equal to m plus 1 lambda over d. So they're adjacent maxima. What we're trying to do is work out the width of this line here. First of all, we know the distance between these two maximas. We've got the delta theta between them, using the small angle approximation that sine theta is approximately theta. So we'll subtract this one away from this one. So we've got m plus 1 lambda over d minus m lambda over d, which gives us lambda over d. And this is theta m plus 1 minus theta m, which gives us the angular separation between. But what we're trying to do is work out the width of this maxima, and we know that there's n of these here because there's the n minima. So that tells us that the width of this maxima, width of the line, is equal to lambda over nd. And so that's, let's call that delta theta lambda. So that's the width here. Now what we're trying to do is to consider lines with different lambdas, different wavelengths, and work out what's the smallest lambda difference that we can have to resolve them. So to resolve lines with different lambdas, we can use that the wavelength difference is equal to lambda 2 minus lambda 1. And so the angular separation of these two lines, which just have different lambdas, will be given by m lambda 2 over d minus m lambda 1 over d, which is equal to m over d times the wavelength separation. Now, to be able to resolve them, we need this separation to be bigger than the line width. If it's not, then these two lines will look like they're exactly on top of each other and we won't be able to resolve them. So we need delta theta lambda, the line width, to be less than or equal to delta theta. When it's equal to, that'll be the resolving limit. So let's just substitute in. We've got this one's lambda and d, and this one is md over delta lambda, times delta lambda. The d's will cancel out and we end up with lambda over delta lambda, which is the percentage uncertainty in lambda, is equal to m times n. And sometimes this is written as R, which is the resolving power or resolution of the diffraction grating. So now we've got that equation, which is also given on your formula sheet. The resolving power is Nm. Now we can use it to work out the minimum wavelength separation. So we can write delta lambda is equal to lambda over mn, and just substituting in, we're told that the wavelength is 500 nanometers, so 500 times 10 to the minus 9. We're told that these are third order maximum, so m is 3, and n is the number of lines in the diffraction grating. Our diffraction grating is 60 millimeters wide, and we've got 6 times 10 to the 5 rulings per meter. So multiplying these two together will give us the number of lines in the diffraction grating. So solving that on the calculator, we get 4.63 times 10 to the minus 12 meters. So if you want, you could write that as 4.63 times 10 to the minus 3 nanometers. Now, part B of this question, that's the answer to part A. Part B says, for this wavelength and this grating, can the resolution be improved? How? To improve the resolution, n is fixed by the grating, lambda is already decided, so the only way we can improve it is to increase m. If we increase m, that will increase R and will decrease the delta lambda, which is what the resolution is referring to. So let's see, can we see m equals 4, the fourth order maximum with this grating? Okay, so if that was the case, we'd have sine theta, just substituting into this formula, will be equal to 4 times lambda, which is 500 times 10 to the minus 9, that's the wavelength we're dealing with, over d. Now, d is the spacing between the lines, so this is equal to 1 over 6 times 10 to the 5. So solving this, we get 1.2. But this is not solvable. We can't have sine theta as 1.2, which tells us that we can't see the fourth order maximum, so it's not possible to increase the resolution of this grating. So not possible to increase R as no m equals 4 at this wavelength. Okay, now we're on to problem 6 for 1221 or 8 for 1231. In this problem, we've got a grating that has 40,000 rulings, so n is equal to 40,000, and the length of the grating is equal to 75 millimeters. And we're asked in A, what is its expected dispersion D for sodium light with a wavelength equal to 589 millimeters in the first three orders? And we're told that the dispersion D is equal to d theta, d lambda. So as it's a grating, we know that our maxima obey the equation d sine theta is equal to m lambda. So we can write this, because we're trying to do d theta, d lambda, let's write this as lambda is equal to d over m sine theta, which tells us that if we differentiate this with respect to theta, d theta, d lambda d theta is equal to d on m, that's constant, and then we do sine theta d theta, which gives us cos theta. Now d theta d lambda is the inverse of d, so we can write this as 1 over d, where capital D is the dispersion, which we're asked to find, and so we have d is equal to m over d cos theta. So we need to find the dispersion for the first order, second order, and third order. So need to find d1, d2, and d3. So we'll just need to change the m's, but our thetas are also going to change. So the first step is going to be finding the thetas. So theta 1, now this is just solving this equation here with m is equal to 1. So theta 1 will be the inverse sine of lambda over d. So this is the inverse sine of 589 times 10 to the minus 9 over d, which is the spacing between the lines. So d will be equal to 75 times 10 to the minus 3 over 40,000, which is equal to 1.875 times 10 to the minus 6 meters. So this is over 1.875 times 10 to the minus 6. Solving this on the calculator, we get 18.3 degrees, and then substituting this in, we've got d1 is equal to 1 over d, which is 1.875 times 10 to the minus 6, times cos of 18.3. So solving that on the calculator, we get 5.62 times 10 to the 5 inverse meters. Now we need to find d2, so theta 2 is equal to the inverse sine of m lambda, so 2 times 589 times 10 to the minus 9 over 1.875 times 10 to the minus 6. Solving this, we get that theta 2 is equal to 38.9, and so d2 is equal to 2 over 1.875 times 10 to the minus 6 times cos of 38.9. And solving this on the calculator, we get 1.37 times 10 to the 6 inverse meters. And then finally, theta 3 is equal to inverse sine of 3 times 589 times 10 to the minus 9 over 1.875 times 10 to the minus 6. Solving this, we get theta 3 is equal to 70.4, which tells us that d3 is equal to 3 over 1.875 times 10 to the minus 6 times cos of 70.4, and solving that, we get 4.78 times 10 to the 6 inverse meters. And that's the answer to part A. In part B, we're asked what is the resolving power in these orders. Well, to do that, we just need to use the equation that the resolving power is equal to m times n. And we've got n here, it's 40,000. So in order 1, R1, we've got 40,000. In the second order, we just times this by 2, so we get 80,000. And in the third order, we multiply 40,000 by 3, so we get 120,000. And that's the answer to that problem, and that's the end of this video.